Now on, let's assume we didn't when we defined it the first time because we were just playing around with very general properties, but let's assume that alpha is an increasing function. Of course, x would be an increasing function. What this means is, well, think of what if alpha was allowed to be an arbitrary function and increased for a while and then decreased, it would mean the weight out there somewhere on the x-axis was actually being negative for a long way. And that would confuse us. We like alphas to be positive. So let's assume that from now on, henceforth. Okay. We define upper and lower Stieltjes sums as follows. Given f, defined on AB. F may or may not be Stieltjes integrable. We're just going to form the sums anyway. And, it may be that f is integrable. We don't know. Let's let f be some function that's defined on the closed interval A and B. And P is partition in the family of possible partitions, and what can we call that? I'm not sure. There's sort of Gothic P is the family of partitions that are possible for AP. And alpha is the integrator, which is assumed to be monotonic increasing. Then this is what's possible. The upper sum relative to f, the partition, and the integrator is equal to the sum of the partition mi delta alpha I, where mi is defined to be the supremum on x I minus 1 x I f of x. The delta alpha I is defined to be alpha of x at I minus alpha at x, so I minus alpha x I minus 1. Okay. So this is the majoring for every little subinterval that the partition induces. So pictorially, what's this look like? If this is f, and of course alpha is lurking around here, it's just a function, a weight that we're putting on the x-axis. So if we have a partition element like this, if this is x of I minus 1 x I, that of course is delta x sub I, and then if you put the weight on it, you get delta alpha sub I. And then I would find mi to be the supremum of the f's on that particular subinterval. And coincidentally, I would just say little m sub I is the inferior, right? So the upper sum, if we have a partition from A to B, is just the sum of, in this case, the majorizing rectangles. So the area under the curve would be completely inside the shaded rectangles that we would rect in, right? Okay. Now what do you suppose? Tell me then what the lower Stieltjes sum of f with respect to the partition and integrated function alpha would be. It would be the sum over the partition of the middle ones, right? Okay. Now, so it would be these guys and somewhat here, going this way. So the sum of all those rectangles, you would see if you constructed all these and shaded them in, you would see that the shaded area is completely underneath the completely underneath the curve. The MI is completely over the top. I was just thinking maybe there could be some weird thing at the end where it flopped, but that's not here. You know, it could be the M sub, little m sub I for this one, but the thing dropped off so rapidly, I don't know what next to it, but then it hits super B, or then it would be way down there, super B. Okay. So that's the deal. All right. So we have upper sums and lower sums. If we refine partitions, let's get this out of the way right now. If we refine a partition, what happens to the size of an upper sum, the size of a lower sum? Which way do they move? The uppers go down and the downers go up. Can we prove that? What's it take to prove it? Do I need to consider arbitrarily finitely many points or just one extra point? Remember, the great thing about partitions is they're finite selections of points. So if I can prove it for one additional point, if I have a partition and the partition starred is the original partition with one extra point, that immediately, inductively generalizes to any finite number of extra points.
The one anything you do in analysis is just one extra point.
That's all you need to do for that reason. For that very reason. Yeah, probably. Did you do it for the Riemann or Stieltjes case? Riemann's case. Well, there's a lot of parallels here. There's a lot of parallels. So, okay, how do we prove that? Can we prove that sort of nothing like a good diagram. Okay. So if I add a new point, say x,
J.
huh?
It's a J.
Okay, x of j. I was going to put a caret over the top. You want j. X of j. What would that do? It wouldn't touch anything outside, right? The piece of the Riemann Stieltjes sum outside of this particular original.
F of x of j has to be between the square and the beginning of x.
Yeah, right. Right. Absolutely. So if we track this up, it's here, and so the MI that's appropriate for this subinterval is still the original MI. The MI that's appropriate for the J one is, I'll put a J after it, is that one now, right? If, let's try to, okay, that's the picture. Let's try to reason this out. Is this always the way it happens? I mean, the function could be going up, it could be going sideways, it could be doing many things there. This, as you said, Dave, this is the max over the entire thing. So whatever you do, it's only going to be less, right? This is the min over the entire thing. Whatever you do, it's only going to be more,
Right.
Okay, that's the guts of the argument. And you can put some algebra down to make that look more impressive, but that's the argument. Adding one more point never takes you higher than mi or lower than little mi. And the sum of the width of the interval here is the same. Of course, we're placing the alpha function on these. We're weighting these things with the alpha function. Is there a problem there? You know, what if all the weight? What if alpha were changing very rapidly here and not so rapidly here? Would that affect anything? We better check that out. This is not something you need to consider for the Riemann case. That would just be the x's. But here, why don't we write down the old contribution to the Stieltjes sum and then we do it?
Why would inserting x of j choose the rate of which element?
It doesn't.
It doesn't.
It doesn't, but it changes. You have a new product. You have this times this thing with the original weight. Now you have this, which is the originally weighted interval, but with a new max.
Right.
This weight certainly didn't go up. This went down.
Right.
So the contribution, this is what I wanted to, this is what I'd like to say. Mi delta alpha I is greater than or equal to mj. This is going to be delta alpha j when we weight it, right? And what shall this one be? Delta alpha j prime. We can't call it delta alpha I anymore, right? So mj times delta alpha j plus, oh sorry, that was mi.
Yeah.
Sure.
I
She must